So is it working now, or can you hear me? Maybe he can't. So Ratnakar, can you hear me?
Yes.
Oh. Okay, so let me start with this thing. Yeah. So for this one, so we were left with the thing to prove that for an arbitrary n, these two, for an arbitrary n, these two transition systems. The first one is Tsn, the other one is Ts prime of n. Cannot distinguish between formulas. I mean, every formula of size n less than or equal to 0 will behave the same way on the two things. Okay, so that's what we have to show. Right. So once we show that, and since these two, they do distinguish f of g of a, so then that means then we can always construct for any formula, CTL formula of size n, something, a transition system on which that formula is formula of that's any formula of that size cannot distinguish over these two transition systems, but still fg of a is true for one and fg of a is not true for the other. Okay. So why does this system for any n for any, I mean, cannot distinguish formulas of up to size n. Can anyone, apart from explaining? So let's start with for n is equal to 0. So in this and this, so formulas of size. So if you could see on the right side. Okay, do you understand the question that I'm asking? Hello?
Could you repeat?
Yes, so every formula that is satisfied by the first model will also be satisfied by the second model.
Yeah, I mean,
Equisense.
For the base case, it does, no? So here the formulas of size 0 are just a and not a. Okay, so that's what I've said. I've indicated here. So for n is equal to 0, we are comparing these two, correct? So, and what we have to show is that those two do not distinguish, they are indistinguishable on all formulas of size equal to 0. Size equal to 0 corresponds to A and not A. Those are the only two formulas. Okay, and so on. So assuming that they are indistinguishable on a transition system of size n, then you have to, I mean, it's the n minus 1, you have to show for for n. Okay, and the reason, I mean, for n. Okay, so why is, so if you could see, pretty much see each of these two, they have the same value. See, for ax, ex of a, ax of some formula f, okay, of size n minus 1, ex of some formula f of size n minus 1, af of f, ef of some formula of of one smaller size, the truth value of that will remain the same, okay, no matter what the n is. So in this case, these formulas, ax of f, ex of f, and af of f, not only do they preserve the truth value of the formula f when you increase it by n, but it also is preserved for ax, ex, and ef. I mean, it is preserved for both, okay? In the case of ax, ex, and af, they, it's originally true, and it remains to be true. Why? Because, as you can see, how is, if it is true for, it's true for f, because, the structure of the two system, the reason that the reason that they were true for n minus 1 is still true for for n, because there is only one path starting from the initial state. If you look at ax, for example, so there is only one path, and f is true for the smaller thing, and because and every path goes through the initial state of the next of the smaller transition system, and therefore it ends up preserving that. In the case of AF and F, because it goes through that path, for which F is true, and therefore so all these things, AF, and I should include EF also here. That will be true. So the reason for these things being false will is applicable even when you extend this by 1, because AX, EX, AX of not A, and AG, EG, and AG, all of them are, I'm missing AG of, AG, EG, no, I'm not missing anything. AG of A, they're all, the reason that they become false is because A itself, AG of A itself is false in the initial state. And you will see that there is always a path, even with this extension, in which there is a state in which A will be false. Okay, so and that's the reason that you will see that the truth value of each of these things is preserved. Even when you increase the size. When you increase the transition system size, it preserves not only the original formulas of size n-1, but all formulas of size n is also preserved, because these are the ways you can construct the larger formula from the smaller formula. Okay, and the reason is exactly this thing that I have mentioned here, because this is just adding this one transition, and and the reason for why those things should have the same value is equally applicable even when you extend it, and that's the reason. And you can actually confirm that from 1 to 2 and so on. Okay, I mean just to confirm it, it's precisely this reason that all of them will pass through either the initial this single state A, or the otherwise when it is false because it is false right there in the initial state itself, or all the paths that made the thing to be false will continue to be paths on which that will be there from the new transition system. So any questions there? So is that argument clear? Yeah. Yeah, and I think you can see that by going from, if so whenever subformula of size n-1, if it is true for that, then it'll continue to be true when you add ax, ex, and af on transition of size n. Okay, and that's the reason, because ax of f will be true, because so that's the only state, correct? So the only successor is this in both cases. Okay, and things like ag, etc., they are not true for I mean, either they are not true because they become false when in the case of A, because it starts with not A. But for the case where AG of not A, I mean, it is true in the initial state here, and it is true, for the smaller thing there, and therefore, it continues to be true. Okay, that's the reason that this kind of extension will will make these two not distinguishable. Okay, on the on the two things. Yeah. Yeah. So the fact that yes.
In the F11 formula, both AGA and the AG not A are both unsatisfiable.
Correct.
I get it, because every node should satisfy not A, but some node satisfies it. Okay. Okay, so I get it now.
Yeah, your question is why should both AG of A and AG of not A should be false?
Yeah, that was I initially thought, but they are not like complete complements.
Yeah, the AG of A is false because A is false right in the initial state itself. Okay.
So now we get the AG of not A, the second state.
Yeah, in the second state, it will be false. Okay, and that's why it will preserve. Yeah. Okay, good. So that is one way. I mean, you could see. I mean, I wanted you to kind of try and understand this, so to give you an idea of how you could prove non-expressibility of some LTL expressibility of the non-existence of a CTL formula for certain non-expressibility of certain LTL formulas. And the way that you do is by showing that there is always, for larger and larger CTL formulas, you have to show the existence of two systems. Now, I think as an exercise, this is something that I will ask you to do, and that will be will be part of the next assignment as well. My next assignment will be on property on LTL, on these logics, their use in specifying properties, and their semantics, as well as these notions of equivalence and expressibility that I have, that we are going through. See, there is an other thing for which this is not true. So it would be instructive for you to recreate this proof for another example. Let me see if I have that example listed here and use that as yeah. See, for example, this one. See, f of A and XA is not expressible. This is a fairly simple formula. Okay, it requires that eventually this LTL formula, it requires that eventually you should get to a point where A is true at that point, and A is true in the at the point next to it. Okay, but that is not the same as, that is not equivalent to f of A and AX of A. And it turns out that this is another instance of an LTL formula that is not expressible in CTL. Okay. Now, there is, Ketoven's book has that chapter 6.3. See, this particular transition system can be used to show, it distinguishes, can be used to, this is a transition system that on which f of A, by the way, there's a notation, a slight difference in notation in the way Ketoven uses. He uses for all and exists, and diamond for F, and the circle for X. So this you should read as AF of A and AX of A. So he is, so the book already has an example of a transition system on which these two, the formula F of A and X of A, the LTL formula, is true, but AX, A and AF of A and AX of A is false. What I want you to do is prove that I mean, yeah, similar to construct a proof that f of a and x of a is indeed not expressible in CTL by constructing a proof for that formula, similar to the way that it was done for f of g, the persistence property. That is the exercise, which means that you have to construct two things on which this formula f of xa and x of a is true, and you have to construct two transition systems, and then kind of find a way of extending that. Okay, and I've also not done it. You can do it, and I'm sure these kinds of things you could probably do a search on the net and then get it. So what I'm asking is, why don't you try and construct a proof, okay, yourself, something similar, which means that you will have to find a way to construct a series of transition systems, okay, that are indistinguishable, that do not distinguish any CTL formulas of size n, yet they distinguish f of the LTL formula, f of a and f of a and x of a. Okay, and that shows. So you can, at least for your intuition, you can use this transition system. This is one that shows they are not, the two are not equivalent. Okay, but that shows that AF of A and AX of A is not expressible as LTL, but the reverse of it, that F of A and AX of A is not expressible in CTL by any CTL formula. The proof of that will have to be based on that construction. So, maybe we can, you can, as an exercise, do that. Yeah. And, we will, we can even discuss in class, because we have a small class and I want to try certain things. It seems like, so it's a small class. I'm spending more time in this expressibility issue and proof of certain things a lot more than I used to in my previous model checking courses, where I concentrated a little bit more on building prototype model checkers for new algorithms, which we will do as well. But since we are spending more time in these expressibility issues, that I thought that we might also try and do it so that we can learn things. Okay, so I will describe it. So basically, what is that clear? Okay, I will make a description of the problem, but what I want you to do is have a proof of this one. This is the assignment. Okay, to show that f of a and x of a is not representable in CTL. The transition system example that I showed in Petoen already shows why these two things are not equivalent. Okay, but what I want is for you to show that in CTL this is not represented. Okay. So that will involve two things. One is constructing some two transition systems, a parameterized transition system that distinguish f of a and x of a, but can never distinguish any CTL formulas of size n. So that is the exercise. Okay. Okay, so let me move on. What is it that I want to do next? Okay, so, in the last class, in one of the earlier classes, not the last class, the one before that, we discussed this example of expressing things under, for this system to prove that for all, if you restrict yourself to only a subset of fair paths, those in which turn equals 0 and turn equals 1 happen infinitely often, then this starvation freedom property, which states that each process will get to its critical location, CR, infinitely often, cannot be expressed, that property, that cannot be expressed as in CTL, okay? Because this will involve, first of all, yeah, so, and that's what I want to elaborate. I sent you an email, okay? So, is that, I hope that, proving that something, say you have GF of, that GF means something happens infinitely often under the condition that as long as something else happens infinitely often, okay? Expressing that in this fashion, AG of AF of P, that is not equivalent to. So in LTL, you can easily express that. You can just say GF of, a turn equal to 0 implies GF of the PC being equal to NC1, okay? But, this thing of expressing this AG of AF of a P implies some AG of AF of some other condition in the CTL formula is not equivalent to that. I don't know, maybe I have it here. So do you remember that? No? So I want to, and in my email, I thought expressed that. I don't know if I have it here. You remember that thing? So, and why that is the case? You have to be a little bit more expressive for me to help me out. What did I do? So I'm not...
Remember that email I forgot the reasons though.
Okay.
Yeah, I'm also not sure about it.
Okay, so let me go through this slide completely, and we'll get back to that. Okay, so maybe this will be clear in this case. Okay, so firstly, so what is model checking under fairness? Okay, so we want to verify, if you want to verify some properties of the kind, eventually something happens. But sometimes they are not true for all parts in your transition system, but they are only true for certain subset of the parts. So the question is, firstly, how do you restrict yourself the checking of a problem? How do you express the fact that you need to check it only on a certain subset of parts which are considered as fair? Okay, because a fair. So you first, it requires you to express a fairness condition, which usually involves certain event happens infinitely often on certain parts. Okay. Under that assumption only, I want to check if another property, this is usually applies to things of like eventuality property. Okay, so maybe I should get to this after I introduce liveness and fairness. Maybe that is a better way for you to for us to understand. But let me get to that. So there are two things that I wanted to cover in here. So let's read this, come to this after that. Okay. So let me go to. Okay, so first, let me cover. I'll revisit the fairness thing. What I want to do is introduce certain laws of equality over LTL formulas, as well as this notion of a normal form, specifically the negation normal form for this things. Okay, so that will give you some extra insight, additional insight into what things are equal and what things are not equal on formulas. And as I mentioned in the last class, you could use these laws of equality also on them. These laws are not as extensively covered in Clark and Cronin's textbook, but they are very extensively discussed in Catone's book in the chapter on CTL. It has a chapter on CTL as well as LTL. This is chapter 4 and chapter 5 of Catone's book. So there he discusses these laws, and I'm using that to as the reference. So I expect you to, for you to understand the material that is in the slide, and then you can use material in those two chapters of Catone's book as a supplement textbook. Okay, so now I will introduce those laws. So some of this you've already probably seen. Okay. Is this the first one? Yes, correct. Okay, first on some equality laws for LTL. Okay. So f of f is equal to true until f, or not f until f. Correct?
Yes, sir.
Okay, this we've already seen. So which means, so also these laws, through these laws, you can also see f is the eventuality operator, linear temporal eventuality operator is a derived operator, because you can always express it in terms of until. Okay. Similarly, G of F can be expressed as that it is not the case that it is never the case that eventually not of F, the negation of F will will happen. Okay, so G is also a derived operator and can be expressed in terms of until. Correct. So G of F requires that F continuously hold at every point on a path, and this is saying that it should not be the case, that eventually you should get to a point not of F. Correct?
So
Yes.
the last one should be true until not F, right? Because FF is equal to true until F.
This has to be not of F. Correct. Yeah, that's a typo. You see that the R operator, the release operator, can also be expressed using the until operator. We will see, okay, in a short while as to why this is the case. So this means that you can do away with these three operators and then have everything expressed in terms of X, negation, until. Okay. Of course, if you have negation, you do, and you can either include or and. You could throw away the and also. So this set of operators, this is is universal, and this can be these can be construed as derived operators. So sometimes, maybe you can, if you have formulas which have F and G, you can convert them using these things into until, and then check the equivalence. Okay. Of course, you will have to have ways of checking equivalence. Okay, over these formulas independently. Okay, and obviously, as we said, for that you will have to have a way of establishing equivalences has to be done on by proving that the words of this formula on the left side is equal to the set of traces satisfied by the formula on the right side. Okay, so you will have to work on the structure of these traces themselves, some induction on the structure of the traces that make these things to true in order to actually prove that. Okay, maybe we will get to that. Okay, as as another exercise, but for now, let's try to understand these equivalences in an intuitive way. So there is this question of how do you actually prove them? Okay, in a formal way. But for now, let's try to understand based on our semantics, the formal semantics of the thing in an informal way. So now we have duality laws. Okay, the ones that actually define negation of various LTL formulas, and they actually serve a purpose of pushing the negation inward. Okay, and there is a motivation for this because we want to get to something called negation normal form, in which the negation appears only at the leaf level. Okay, so not of G of phi is equivalent to F of not of phi. Correct? Okay, because saying that, yeah, phi does not hold continuously on any trace means that not of F should eventually hold. Okay. Similarly, not of f of phi is equal to g of naught of phi. Similarly, you can push naught inward. Okay. So x of phi is not true if it is the case that the next state, the next point, the negation of phi is naught of phi is true in the next state. Yeah, these two laws we will see how you could use. You know, so until and R are kind of dual operators, just like and, the logical and or are dual with respect to negation. Okay, so naught of f until psi, you can push the negation by using the R operator and vice versa. And we will see why these two things are equivalent, because in a few slides down the line. Okay, this you already know. Okay, this is the usual logical connector. So now, so with these set of equivalences, any LTL formula, an LTL formula phi is said to be in negation normal form when only if naught appears only at the atomic, I mean on at the leaf. Okay, so negation can be used only on the atomic level, on propositions. Okay, so for example, this one. So what I have. Yeah, this one is in NNF. Okay, assuming F, G, and H are atomic propositions here, the first formula is in negation normal form, whereas the second one is not, okay, because their negation appears at a non-atomic level. So you could use these duality laws to get an arbitrary LTL formula in a negation normal form, okay? Assuming you are allowed certain subset of temporal operators. For example, any LTL formula phi has an equivalent formula F prime, an equivalent formula in negation normal form containing only X, U, and R, okay? Because you can use that. As you see, U and R are dual of each other, okay? And as you can see, F, G and F can be expressed in terms of U, but in order to push the negation inside, you do need R and U. So if you're allowed X, U, and R, you can always push the negation down. So you can have a negation normal formula. That are another ways you should allow G. If you allow G, then you can also do that, okay, because as you can see, you can get rid of F, because eventually you will have, as long as you can have G, because G of F can be expressed in this, and that's why you need a G as well, okay? So using these duality laws, you can get things in negation normal form using these operators, yeah? So I hope that you understand the these duality laws, except the ones that relate R and U, and that's the one that I will get to in the next slide. Okay, any questions here? Okay. Okay, so R and U, I mean, R is a dual of U in the sense that the negation of one can be expressed in terms of R by just like these De Morgan law. This is the kind of De Morgan law equivalent on linear temporal operators. So what is not of F until G? Intuitively, see, F until G has two constraints, correct? Ratnakar, what are the two constraints F until G imposes on traces?
F has to be true until some point, and that point is when you see the G.
Yeah, in addition to that, there is an additional constraint. It requires that G must be eventually true. Okay, that's very important. Till G requires that G is eventually true, and up to the point prior to when G becomes true the first time, F has to hold continuously. Okay, so there are two constraints there. So there is an eventuality constraint on G as well. Okay, so that's the one that you missed. Okay, yeah, you should be yes, guys should understand that. Okay, so the negation of F until G means that it includes those traces in which the constraint that Ratnakar just now explained gets violated. That is, F will become false too early. It stops to hold too early, that it becomes false even before G becomes true for the first time. Or there is a case when G never, okay, not G is true continuously. Okay, so these are the two kinds of traces that are included in not of F until G. Clear? You agree? Any question there? Yeah, so this part here I have done. Not G is continuously holds up to and including the first time not F becomes true. Okay, so that's what this means. F stops to hold too early. Okay, so the first time that G becomes true, that is not G is continuously true, and at that point not that F becomes false. Okay, so this is actually can be expressed as you can push not inside. Okay, in terms of, you can express it in terms of until itself, G of not of G, or there's a point at which you see even before there is a point at which F becomes false, even before when G is still not true, and up to that point, that's the first point at which G becomes it's before the first point. So F continuously holds, okay, not G continuously holds, and then but it stops to hold a little bit too early, even before G holds for the first time. Okay, so that's how you could express F not negation of F until G in terms of until and you need a G as well here. So that's why the negation normal form you could use have push negation inside as long as you allow for G, because if you as long as you allow for G, allow G and you can get them. So but it turns out that this one is exactly not this one on the right side that you, I mean, this whole thing is exactly not F R not of G, okay? I hope you remember the release operator. See, the release operator, PRQ, it says that either Q holds forever or P releases that obligation of Q. The moment, you know, P holds, after that, if P never holds, then Q has to hold forever, okay? But if P holds at any point and Q need not hold, it has to, up to the point, once up after the point that, P, holds, after that, Q need not hold. So when there's a point at which P as well as Q, Q holds, okay? Which means this is what this condition here in square brackets entails, requires. That, you see, there is a point at which F becomes false, at which G is still false. Up to that point, F, was continuing to be holding with that. F became false too soon because G was still false at that time. So this is exactly this condition, not F R of not G. Okay, so this one, if you replace P with not F and Q with not G, this is exactly what you get. Therefore, negation of F until G is equal to pushing the negation inside and replacing R. Okay, and that's why R can also be expressed as a negation of P, not P until not Q. So that is the so the reason why you have these duality between R and U. So you may ask the question as to why have the release operator, since you can anyway, why not just live with G and until, or just with until, if you don't care about negation normal form. What do you think? What is the advantage of having R, you think? Especially from the perspective of having things in negation normal form, okay? I haven't given you an advantage of having LTL and negation normal forms. I will get to that soon. See, if you want to, you can, of course, push the negation, inside the until operator. But you see that you're doing at a cost, okay? Not only are you having this disjunction and you have another disjunction here, and then you are introducing these, conjunction in the formula. This disjunction is the one that is the killer, okay? So if you have whole nested, multiple nested hierarchy of the until operator inside the negation, and if you want to push that negation, you have this size explosion, the size of the formula. Whereas in terms of R, if you allow for R, then you, there is no size explosion because you can push the until, the negation. Even pushing the negation does not increase the size of the formula. Therefore, the size of the negation formula will be, size of the translating an arbitrary LTL formula into negation normal form in the presence of R will be, the size will be more, will be smaller. And that is, one of the reasons to have the release operator. And therefore, if you can devise model checking algorithms directly, are able to deal with the release operator directly, then you can do with working with formulas, especially if there is, assuming there is an advantage to keeping things in negation normal form, which is a property that we'll exploit later on in model checking. Then by having R, you are keeping the size of the negation normal form small. Okay? And that is the motivation for having the R. Okay? Any questions here? Okay. By the way, G can also be expressed just like F can be expressed in terms of until G is as true until F, G of G is false until, false releases G. Okay. If you have false here, the second part of this thing is reduces to false, and the only thing you will have is G, that the G has to hold good forever. Okay, and that's why you will have, these are two ways of expressing G of this forever operator you can express in terms of R. So universality, just like you had a bunch of universal operators, you can now have, so you can extend that to path, quantifiers as well. So you saw that not R, X, and U are a universal set of temporal operators in the sense all the rest can be derived in terms of them. And similarly, it is enough to have the existential path quantifying operator, okay, and you can do away with with A, and then the reason is, as you know, existential, a universal quantifier can be expressed in terms of an existential quantifier as negation of an existential quantifier, and that is the property that we actually use to derive formulas, to transform formulas with universal path quantifiers into one with existential quantifier. Okay. So this is just the all this we already had. So the new one that I'm choosing is A of F. So now we're getting into CTL and CTL star territory. Okay, so these are some universality of CTL operators is what we will be getting here. So A of F can always be expressed in terms of E by having this negation. Okay, so yeah. So state on which every path F is true is equivalent to saying that there does not exist a path originating from that state. It's not the case that there exists a path in which not of F is true. Okay, so that is what it is. So these things we have seen. So this is simple. That's the way that you do. So So you can always get rid of the universal path quantifier, and that's not very surprising. But what is interesting is using the duality laws over this, the duality between A and E path quantifier and the rest of the things you can now get over CTL operators. Okay, so here is something, I just described it for the path quantifier independently. Now, I'm going to be introducing some duality laws and universality for over CTL operators. So the CTL operators EX, EG, EU, and ER are sufficient. Okay, obviously you can basically what I'm saying is you can get rid of the fact that you can get rid of A. You already saw. Okay, but the question is that you can actually express it in terms of just these CTL operators EX, EG, EU, and ER, because you remember that the CTL operators, just by doing this, you are no longer necessarily within CTL, because when you have E applied to something which is a negation, that's not necessarily, that may not produce, that's not a standard well-formed CTL notation. So, but it turns out that you can get rid of AX, all the universal version of CTL operators, where the universal quantifier is juxtaposed prior to the temporal operator. That's because you can see that AX of that's what these rules describe. These are equivalents over CTL formulas. So AX of F can always be expressed as not of EX of not of F. As you already saw, that A can be replaced with E, not of E, not of X of F, and the duality of X operator allows you to push this negation inward. So by getting not of EX of not of X. Okay, that's what this thing says. So intuitively, it says that should never be the case that any of the, so here this insists that every successor state should be such it satisfies F. This says that there should not be any successor state in which not of F should be true. So similarly, you can have no. This thing is yeah. I didn't mean to say EF. I mean, this is superfluous. So just look at AG. So AG is not of E, not of G of F, which can then be converted into not of EF of not of F. Okay, it basically says that it should not be the case. Eventually, you will get to a point where if there is any, it should not be. There must not be a path in which should not exist a path in which eventually not of F becomes true. So that's how you can get rid of this. Similarly, AF of F can be replaced with negation applied to EG of F, because EG, forever, any existence of a path in which not of F continuously holds is a violation is a violation of the fact that eventually there is a path in which eventually F holds. Okay? Yeah, so all I'm doing here is applying the duality, using the duality of E, and then pushing the negation using the duality laws of this. And therefore, you can now do, you can express it in terms of ER. Okay? Yeah, so these laws are there. Yeah, you can also get rid of ER by expressing in terms of EU, in terms of EU, but the disadvantage of that is the same, okay? That you have a kind of a branching thing in here due to these extra things, and therefore the size of the formula is, the transformed formula can be exponentially larger when compared to the original size of the formula, where by size I mean counting the number of connectives in the formula, and that's why it is useful to include E of R. And that's why you will see, we will exploit this, all our model checking algorithms, because these form a universal CTL operators are model checking algorithms, and even in their implementation, they always are expressed by concentrating, by dealing or handling just these set of operators. Once you're able to check formulas whose root has these CTL operators, you automatically get the A version of it by just taking the negation of it. Okay, so the negation of it. But for a CTL formula, which are, and this is true for any state formulas, taking the negation is not that difficult as opposed to path formulas, because negating state formulas is just taking the complement of the set of states. So it's not as important to so more laws, okay? So any questions here on the CTL operators thing? Yeah? Okay. So here are some more laws, okay? So these are called absorption laws. So sometimes, yeah, I mean, repeated G's, etc., can be removed. G of phi is the same as G of phi. F of phi is phi, and if you have F phi until phi, that is equivalent to phi. Why? So if you intuitively, it doesn't make sense. If you think it doesn't make sense, you have to raise your hand. So this you're convinced, no? Why is this the case?
Yes.
Okay. How about this?
Yeah, yes.
Why?
Because it's 5 until 5. Right? So in the first state itself,
Yes, correct.
you get a 5 because
Yeah. How about this one?
Yeah, same thing. We can apply the third law.
Yeah,
to the
because
second.
yeah, but this is slightly different than that there, because psi should eventually hold, because it requires, phi should continuously hold anyway, right? Therefore, so this one will say that, okay, phi has to hold until this one holds, and the other one is saying, phi has to hold until psi. It's not because of, psi will eventually have to hold, and since phi has to continuously hold, this is, it's already the case that phi is continuously, the second phi is redundant, because the first phi will superimpose the second phi. And yeah, that, and why, how about this? Why is this?
again, like phi until psi is already given inside. So we have found a psi. So then again we are saying until psi. So doesn't make sense. Just one psi is enough.
Yeah, once psi becomes true, yes, so the entire formula is true anyway, correct? So therefore, one side becomes true. So this is, yeah, because this is somewhat similar to this reason. So one side becomes true, you can, the rest of the trace can be arbitrary, okay? And this also says the same thing, okay? So once psi becomes true, so after that, it doesn't matter. And therefore, that's the thing. So, you know, this is saying phi happens infinitely often on a trace, then f eventually will is equal in getting that. What's the explanation, intuitive explanation for this?
Like G of phi gives says that phi happens infinitely often, right? So then just saying eventually that happens doesn't make any sense because it already happens infinitely often. So saying eventually doesn't.
Correct, because this is just superfluous because the moment once it happens, it's done. Okay? So this is applies for G of f of G for the persistence property, because once the same f of G, the point at which G, the point at which eventually phi continuously holds, all the points prior to that, here I'm looking at this, are overtaken anyway, because all those of any path, so all the paths, since you know that, so once, every state has to satisfy f of G of phi. So since there is a point at which eventually G continuously holds, all the points prior to that are also covered anyway, because all those things also, it is true, they satisfy the f of G of phi, because f is that covers all the states prior to that as as well. What would be interesting is, so these laws, I mean, I'm actually doing this in terms, intuitively. How exactly, I mean, I kind of repeated this point. How do you formally show these things are equivalent? It's something that we will maybe revisit. Okay, so these are some distributive laws. Okay, so here, and you have to kind of review. I suggest that you review these things and convince yourself. I mean, I may not go through all of them, and so let's do one, and then maybe you can convince the other. I have forgotten what. So this one, F distributes over R. The eventuality operator distributes over R. Correct? If it is eventually the case, eventually you get to a state either phi or psi is true. Every such trace that satisfies f of phi, f of phi necessarily satisfies f of phi of psi, because phi is eventually true on that. Correct? Yeah. So this is union of two traces. Okay. So traces on which eventually there is a state where phi holds. So that's the case, and it is since phi or psi also holds in that state. That's why that F of phi of psi also includes that trace. And similarly for, for this. But this is not true for G. Why?
Because we just need phi or psi to be true at every single state, but we don't need phi to be true globally or that psi be globally. We can have an alternating combination for it.
Correct. They can happen at two different. Yeah, because G of phi can continuously so yes, G of what's the explanation? Why? No, this and is true. So this is not true for G because you have G phi or psi. So it is globally true that in every state phi or psi holds. Yeah. Well, yes. Yeah. But if G continuously holds for psi, yeah, but see, this one, correct.
Like we could have states alternating with psi and phi.
Yeah, I think that's what
the left side will be
Ratnakar said. Huh? So that's
yeah.
why. So, but the right side has fewer thing. Huh? The right side, is it a subset? Okay. The right side has fewer, correct?
Yeah, right implies left, but left doesn't imply right.
That's right. Yes. Yeah. Is it true for X?
Yes.
Yeah. That's correct. Yeah, and the dual of that is as well. So AG distributes over conjunction, but not the other way around. So please do spend some time in convincing yourself these things. Okay, by drawing. Yeah,
Sir, I didn't understand why the second law is not true for F. I think
one?
F also should distribute. Yeah.
I only asked the question if it is true for X. I never claimed that it is not true. Oh, you're disputing why it's not true for F?
Yeah.
Yeah, I think it's for the same reason. See, F of G and psi will mean that eventually you should have a state in which both, I'm sorry. Yeah. So so eventually you will get a state in which both simultaneously hold.
Oh, sorry. Yeah.
Correct?
Yeah.
But if you replace F here, yeah, so you can have it in two different points. That's why. Yeah. So these are similar ones for AG and AF. Yes, this is not true for AFF, and that's what this example shows. So I will leave it to you since we are so I'm running out of time. So I want to introduce a few more laws and lecture here. So I will visit. So these are called expansion laws. Okay. They kind of expand until operator as a series of x's. So F until psi is equivalent to saying either psi is true now or phi is true now and in the next state you have phi until psi to be true. So if psi is true, then it is done. Otherwise, we have to have phi to be true, and in the next state, phi until psi. Okay. So a lot of the previous laws, some of the previous laws, can actually be proved using these expansion laws. Okay, because this effectively gives you a way of showing, you look, so usually this equivalence is one way to prove. I don't know if that's the only way. Showing is assuming it's true for all, true for a set of paths. Then, if you extend that by one more, it will still continue. The equivalence still continues to hold good, and I think that is one way to do. Okay, and that you could do for CTL also. I mean, because I know Ratnakar asked this question. Okay, it is not, to visualize these things, but when you want to prove equivalence of formulas, you will have to prove them on either traces, linear traces, or trees, okay? And you will have to use some kind of either induction or extension things to do. And this, I'm saying that it gives a certain way of doing it. And these are, that's why I call it expansion laws. And you see that here, until is defined in terms of, until, but for a, longer, a trace, or you could say one shorter trace, okay, until, psi becomes true. So it's kind of iterating over the traces, and that's what these things say. So similarly, but for F, so the F and G are kind of the same versions of this thing. For CTL operators, you can have something similar. Okay, A of phi until psi is true. If psi is true in the first state itself, then you're done. Or phi has to be true in the first in the root state, and every successor of that state, immediate successor, you should have AF until psi to be true. Whereas F will have the disjunction. Okay. E is exactly similar to that, except that A is replaced by E. Okay, so if no more questions, I want to end by introducing this classification of this thing. Is it here that I have? Okay. See, this is a classification of properties. I will define it for LTL because it kind of fits very well for LTL, linear properties. But you can actually use this, extend this classification for CTL, branching time properties as well. But there are some questions, and I'm going to pose those questions and end today's class, and then have you think about that, and we will revisit that. First of all, a counterexample for an LTL formula. LTL formula is either true for a path or not true, right? And an LTL formula defines a set of paths, okay, is defined, is characterized by the set of paths for which it is true. So when you model check, okay, or even if you can raise this problem, okay, in model check, you will have to find a trace, okay, that does not belong to that, okay? So a counterexample for an LTL formula is a trace that is not true of this LTL formula. So, or in the model checking framework, it must be some trace that is induced by a transition system that is not contained in the interpretation of this formula. That is, so it's a path from an initial state. A counterexample is a path or a trace from an initial state that is a witness to a violation of phi, or from the starting state. So if you're referring to path induced by a transition system, then it has to originate from one of the initial states. So this classification is based on the kind of whether the counterexample, the witness to violation of that formula is finite or infinite or either. Okay. So this counterexample can be, maybe for certain formulas it may always be finite, or for certain class of formulas it may always be infinite, or for certain class of formulas you may have counterexamples, violating instances which are both finite as well as infinite. And that's how safety and liveness properties are, this class of safety and liveness properties. We've already been kind of informally, I've been using those terms. So this is the formal way of defining them. So a safety property is a formula whose violation can always be, whose violation can always be shown by a finite counterexample. For example, these formulas of this kind, their violation can always be shown by finite trace. Why? GP. Because it requires, can someone take a crack? Amin?
Like violation requires lot of
P. I mean, let's start with X. XX speeds, it's easy, huh?
Yeah.
Yeah. So
just next two states will
correct. So G of
should
P.
be not P.
Correct. G of P. Yeah, you were about to
G
say.
of P also, the violation should be not of P, a state with not of P should be present in the path. So that should be present in a finite path.
Prefix. So you can always, if there is a violation, there's always a finite prefix. That's the way to maybe, a better way to put it. If there is a violation of this property by a trace, there'll always be, that violation will always happen, it has to occur in a finite prefix. So it's enough for you to look at some finite prefix. Of course, that length of that finite prefix can be unbounded, okay? Now, and for, and let's suppose that we further restrict our things to finite rate transition systems. I think this can be extended for infinite state systems as well. But yeah, I mean, this concept can be extended. So if it is, yeah, so if it's even for finite state systems, okay? So this kind of classification applies for finite systems, because even for finite state systems, the traces can be infinite, okay? Therefore, you can have, for the moment, let's assume it's a finite state system. So, so you can have counterexamples which are necessarily infinite. So why is this true for P of R of Q? See, P of R of Q has two things. Either not of P holds forever. Okay. Yeah. The violation of this can be yeah. So either
Not
yes,
Q in our first state.
yes,
We can have not P and not Q in our first state, right?
yeah,
That violation.
yeah. So its violation is only those in which you end up having not of P and until Q, because the negation can be converted into until operator. Okay, and it never requires so so you could check that. So in any case, so what you should understand is that the violation of a property. So this is kind of a characterization I'm saying, whether, yeah. So, but try to understand the thing. So the violation is always state of, can be expressed as by a constraint on a finite prefix. Okay. Now, an invariant property is a special kind of safety property. Okay. AG of forget about this thing. I've not paid too much. Yeah. So it is these kinds of things. G of P. Okay. Where P has to be a predicate. For example, this one is not an invariant property. So it's a very, very special kind of safety property. So you just have G and just a proposition, okay, or a predicate. Yeah, just a proposition. So this is a very restricted form of safety property in which it, just says that a certain predicate on a state has to be true, everywhere. Okay. As a matter of fact, both these things. See, one advantage, and the reason that this class of properties is I'm introducing is because it's really motivated. Because checking safety properties and invariant properties can always, this is actually true for any safety property, although I've stated this thing as an invariant property. But for invariant property, this is also true for safety properties. Okay, so an invariant property is a special kind of, that is defined. So an invariant property can always be checked by enumerating just a set of all states reachable from initial states. Okay, so because an invariant property, you could just enumerate all the states, and all you have to check is if it is true. Enumerating all the reachable states from any of the initial states. And then for each of them, that predicate has to be true. Okay. So that is the advantage. Okay. And you can see that even for safety properties that are not invariant, because they are of this kind, okay, you only need to keep track of some finite history. Okay. So, you may need to, you can still do it by enumerating all the reachable states, but you may have to, keep track of some amount of history, okay, a bounded amount of history to check safety properties. And that's why checking safety properties is, or the subclass of safety properties is model checking them is a lot more efficient. And that is the first model checking version of model checking algorithm that we will be looking at starting with next class. And that is why this classification is important. Okay. Now, a liveness property is a formula whose violation cannot always be shown is a liveness property is one in which a counterexample is necessarily, is always infinite. Okay. For example, these kinds of LTL properties, so eventuality things are something that happens infinitely often, but eventually it is the persistence property. They are all liveness properties. So their violation necessarily, because you can always extend. So if for a finite prefix, if you have seen that phi has not happened, it can always happen in the future. So you cannot determine it by just looking at a finite prefix for these kinds of properties. So just try to understand for f of p. Okay, so let's start with simple liveness property, f of p. Okay, I mean, even for that. So you cannot, if I look at only, if I give you just a finite prefix of it, are you convinced?
Yes.
Yeah, yes, yes.
So we can always extend, even if it is not, phi has not been true in any of the states in that prefix. It doesn't mean that it is not. Okay. A violation. How can you witness a violation for a trace for f of phi? I'm just asking that.
If you have an infinite path which does not satisfy that.
Yeah. So for
a loop can be.
Yeah, for a finite, I mean, I was just going to ask, suppose, yeah, what Ratnakar said was certainly applicable for infinite, I mean, yeah, it's an infinite trace, that is correct what is stated. But for finite state systems, since we have seen that every path eventually a state has to repeat after a finite number of things. So if you keep track whether it has looped, so you can. Okay, so I'm just giving these as intuition. So intuitively, but my definition still stands. So you need some additional information whether the path has looped or not. Okay, if you can keep track of that, then you can do it. But that's still that I'm getting away. Okay. From the thing, but this is the characterization of liveness property. And neither is f until, yeah. So where some counterexamples violations are finite, some are not finite. So this is an example of that kind. Because there are some cases where the violation can be noticed, in those cases where G actually happens, after a finite time, and there's a violation because the F becomes false too soon. But then it may be because G never happens, okay? So, yeah, so there'll be some counterexamples of this kind for which you need to look at G. Yeah, I mean, I was just making this observation. For every finite example, every counterexample is always lasso shaped. Okay, so by lasso I mean there is an initial finite tail ending with a loop. And this is, as I make this observation as a special cases, because you can exploit this for finite state systems to be able to kind of in some cases, somewhat efficiently check certain liveness properties as well. Whereas safety properties you can always check by looking at a finite prefix. Okay, therefore they would really, a lot more efficient. But for finite state systems, this property can be used to check a certain class of properties efficiently as well. So here are some questions that I will raise, and for you to think about, and we will discuss next class or in one of the future class. Can you syntactically characterize? By syntactically characterizing, I mean the kind of by looking at the structure of the formula, not necessarily the interpretation of the formula. A subclass, because this definition is kind of not structural. It is about the violating traces. So a subclass of LTL formulas that are guaranteed to be safety properties. Okay, that's the question I'm raising. What is that that class? Okay, and what is similarly? What are the class that characterize a subclass that are all liveness properties? I mean, yes. Can you characterize maximal subclass? I mean, I can add the term maximal also. Okay, LTL formulas that are every member of which is kind of. Can you provide a syntactic characterization of that thing for the LTL formulas? Okay. I think these things must have been done, but I have not. I've looked at it, but I cannot pinpoint to such results right away. So we can think about that. You see, and this classification is obvious for LTL formulas because I've defined the violating counterexample as a trace. Okay, but for CTL or CTL star formula, which is state formulas, of course, you could define it as things because there are some CTL formulas which there is an intersection of LTL and CTL formula. Okay, for them you can automatically extend this classification. But there are CTL formulas that have existential quantification and so on. What does violation of those kinds of CTL formulas that are not representable as LTL formulas, what kind of such a classification can be extended to that? Okay, is my question that I'm raising. Okay, and so this is one nice way to present counterexample for those kinds of CTL formulas. So the general question is, what is a good way to present counterexample violation witnesses to CTL formulas? Okay, so these are some questions for you to think about, and we will discuss this thing. So that's why you will see that if there is a CTL, I mean, you can check this with for LTL formulas. When you check it in USMV, it'll always produce, if it's a safety, it'll produce a finite witness. If it is not, I think you can check if it produces a loop, okay, an infinite trace. And a way that it can produce an infinite trace is by producing a lasso. Okay, that is something that you can check if it produces a lasso for a liveness property. And what does it do for CTL formulas that are not necessarily, they don't belong to this classification? So, for example, properties that have existential path quantifiers, existential path quantifier, the negation will require you to say, oh, all paths originating from these things. So you will have to give witness to violation of existentially quantified path quantified formulas. Necessarily will have to demonstrate a whole bunch of paths. Okay, so which is kind of hard. I mean, or you can take the other extreme. Oh, I'll only show you a state. Okay, and that is that may not be, while that is good enough. Okay, so you can always produce a state for which for which the state formula is false, okay, and be done with it. But you also would like to produce some path, okay, information that is leading to the violation. So this business of what is the best way to present the counterexample to CTL and CTL star formula state formulas is also an interesting thing. That what I don't know is, I mean, I don't know if there has been work in actually discussing this thing, but these are some questions that are natural to ask. Okay, but it's important for you to understand this classification, because that's very important to for the model checking algorithm that we will be incrementally more powerful and more expressive model checking algorithms that we'll be looking at. Yeah. Okay. So I'm going to end here with any questions that you might have. I'll talk about
did you mention that we are going we are lagging behind in the syllabus?
I have to look at that. No, I don't.
Okay. No, I heard you mention it in the class. I thought I heard you. So if you want to go a little quicker, that I think that is fine with the three of us. I mean, this pace is also fine, but if you want to go a little quicker, I think
okay,
the three
so
of
I will do that. Okay, so that is good for you to mention. Okay, so maybe so I so where you could that's good feedback. I will do that. Yeah, I'll keep that in mind. Yeah. Okay, sure. So I'll stop.